You might be wondering what those time lapses of change have to do with calculus, but when you analyze them to the roots it becomes obvious that they are in essence related rates. However, before we look at a real-life application, let's first define a related rate. By definition, related rates are problems that involve finding a rate at which a quantity changes by relating that quantity to other quantities where rates of change are known. Now, to summarize that wordy definition, a related rate is essentially a relationship between two entities that are changing in accordance to one another. That being said, since the rate of change is, by definition, a derivative, one can formulate that a related rate problem is based off the application of derivatives. However, a related rate isn't solely a derivative, but instead the application of implicit differentiation. This allows for a relationship between two variables and their derivatives. Related rates have a wide variety of use and can successfully describe many processes. Let's first take a look at a simple related rates problem using the inflation of a balloon. The first step is to know your given information. Assuming that the balloon is a perfect sphere, you can know that the volume is 4/3 pi r cubed. The given radius is 5 centimeters, and the known change in volume over change in time is 10 centimeters cubed per second. To solve for the change in radius over change in time, you must implicitly differentiate the volume equation. After you implicitly differentiate, you are left with dv over dt equals 4 pi r squared dr over dt. You have now completed the calculus aspect of related rates and are left with the simple algebra to solve for dr dt. To isolate dr dt in terms of dv dt, you must divide dv dt by 4 pi r squared. After that comes simple substitution. You plug in the known radius of 5 centimeters and the known dv dt of 10 centimeters cubed per second and are left with dr dt equals 10 centimeters cubed per second over 4 pi times 5 centimeters squared. After simplifying, the centimeter squared in the denominator reduces the centimeter cubed in the numerator, and you are left with dr dt equals 10 centimeters over 4 pi times 25, and then you can further reduce to get dr dt equals 10 centimeters per second over 100 pi. After calculations, you are finally left with dr dt equals 0.032 centimeters per second. Now that we've defined and completed a basic example of related rates, let's further apply our knowledge to the melting of an ice cream scoop in a cone. Before experimentation, we expected that due to the viscosity of the ice cream, it would not remain spherical as it melts. However, the time-lapse proved this hypothesis wrong and showed that the ice cream cone for the most part remained spherical throughout the melting process. Similar to the balloon, the volume of the ice cream can be found with the equation 4/3 pi r cubed. The other given information for the ice cream is that the radius equals 2 centimeters and dr dt is 0.0625 centimeters per minute as derived from experimentation. Just as before, the next step is to implicitly differentiate the volume equation. This leaves you with dv dt equals 4 pi r squared dr dt. Next, through substitution, you arrive at dv dt equals 4 pi times 2 centimeters squared times 0.0625 centimeters per minute. At the end of calculations, you arrive at the answer dV/dt equals 3.14 centimeters cubed per minute. Now, when you increase the radius and therefore the size of the ice cream sphere, dV/dt is drastically altered. Through experimentation, we found that after doubling the radius size from 2 centimeters to 4 centimeters, the time it took to melt also doubled. This fact proved that dr/dt is a constant. Because of this, the only change in the implicitly differentiated equation is the size of the radius. The new equation reads dV/dt equals 4 pi times 4 centimeters squared times 0.0625 centimeters per minute. After calculations, you are now left with a dV/dt of 12.56 centimeters cubed per second, which is quadruple the dV/dt of the ice cream with a radius of 2 centimeters. Because of this, the only change in the implicitly differentiated equation is the size of the radius. The new equation reads dV/dt equals 4 pi times 4 centimeters squared times 0.0625 centimeters per minute. After calculation, you are now left with a dV/dt of 12.56 centimeters cubed per minute. This is quadruple the dV/dt of the ice cream with a radius of 2 centimeters. To understand this phenomena, you must first look at the volume equation and its derivative. Because dr/dt is a constant, you can observe the derivative of the volume equation as simply 4 pi r squared. While 4 pi r squared represents the derivative of the volume of a sphere, it also represents the surface area of a sphere. This relationship proves to be vital in understanding the variance in the rate at which an ice cream melts. Since dV/dt essentially equals the surface area of the ice cream cone, you can postulate that the change in volume over time has a direct relationship to the surface area of the ice cream cone. When the radius increases, and therefore the surface area increases, you are given a greater dV/dt, which validates the direct correlation between surface area and change in volume. Now, to best understand this relationship between the radius, surface area, and volume, let's view them as graphs. The first graph we will look at is a graph relating the radius to time. Looking at the graph, you can right away decipher that it is linear, and the change in radius according to the change in time remains constant. The slope of the graph itself represents dr/dt and proves that it is a constant of 0.0625 centimeters per minute. The next graphs we will look at are the volume versus time and surface area versus time graphs. Right away it becomes obvious that these two graphs are quite similar. Both graphs are parabolas, which proves that as time progresses the change in volume and surface area does not remain constant. The slope actually decreases as time increases, which proves that the change in volume and surface area decreases as time progresses and the size of the ice cream cone becomes smaller. Lastly, we will look at the graph of change in volume over time versus the change in surface area over time. This graph is similar to the radius versus time graph as linear. The linear shape of the graph proves that the relationship between the two variables is constant, and its positive slope proves that as dV/dt increases, dA/dt also increases. The graph further justifies the point that change in volume and change in surface area have a direct relationship which remains constant over any period of time.